Last time we talked about the isentropic process. First of all, we are talking, our talk is still continuing about the TDS relation. We have developed two equations to calculate delta S. Delta S is equal to delta U over T plus BdV divided by T, and we have another equation which is delta H over T minus VdV divided by T. And we have applied those two relations to calculate delta S if we have actually any working fluid undergo from one initial state to a final state 2. We have applied this actually in case when we have incompressible substance, liquid or solid, and we have learned how to calculate delta S by integrating this equation. Also, we talk about the case when we have an ideal gas, and we said we have two approaches, either the constant specific heat approach or the variable specific heat approach to calculate delta S. And then we talk about the ideal gas. It was the third case when we do have an ideal gas undergo an isentropic process. So isentropic process of an ideal gas. Type isentropic process of an ideal gas. Isentropic, that means actually the change of entropy is equal to 0, or S is equal to constant. S, the system is reversible and adiabatic, so the entropy will be remaining constant in this case. And we said we have two approaches in this case. We talked last time and we have derived this equation in case actually of following the constant specific heat analysis approach or the approximate approach. We call it actually as the approximate approach to calculate the change of, to equate delta S for an isentropic process by equal to 0. We have actually equated this equation which we have developed for the case of constant specific heat analysis. Those two equations we have equated to 0, and then actually we came up actually with those relations. We said T2, if we have an ideal gas undergo an isentropic process, then we can say the final temperature divided by the initial temperature T2 over T1, B2 over B1 to the power K minus 1 over K. K is the specific heat ratio, which is the ratio between Cv over Cv, and this one we calculate from table A to B. Depending on the working fluid, we can get the value of K, which is the specific heat ratio, from table A to B. Table A to B, if you remember, we have subtables, each subtable for a working substance. In addition to this, if the substance is not listed in table A to B, there is table A to A, in which actually at temperature equal to 300, the value of a specific heat and also the specific heat ratio constant is given there. Okay, so if we have an ideal gas undergo an isentropic process following the approximate analysis or constant specific heat analysis, we can equate the equation to 0, and then we can get this relation like what we have developed last time. This is also equal to V1 divided by V2 to the power K minus 1. And this is how we get the change of temperature with the change of pressure and the change actually of the volume if we have an ideal gas undergo an isentropic process. This process will be very important when we talk about the compressor or turbine, especially compressor. If I need to calculate the isentropic efficiency of the compressor, it is the ratio between the actual work divided by the isentropic work. Isentropic or the reversible work or the maximum work. Okay. In this case, I will be considered the compressor undergoes the actual process. Then I can calculate the actual work. Then we can consider the process as isentropic, and in this case, I can also calculate the reversible or the maximum work. Inshallah, today we will learn how to calculate the reversible work as well. But in order to relate for an isentropic process, to relate the change from the initial state to the final state, in this case, we can get the isentropic relation. We can relate the temperature with pressure with volume through this relation. Okay, let's consider the case following actually the exact analysis or the exact approach, which is actually based on the variable specific heat analysis. For the variable specific heat, we have developed an equation to calculate delta S. We said delta S is equal to S naught 2 minus S naught 1 minus R lim B2 over B1. And we said this S naught 2 and S naught 1 are calculated from table A17 to table A25, depending on the working substance. This is the equation that we have calculated. We have proved actually in case when we have an ideal gas undergo actually a process or a change from one initial state to a final state, this is how we can calculate delta S. Those values not one from the tables. And then we have to add the pressure dependent term minus R ln B2 over B1, then we can calculate delta S. But if we have an ideal gas undergo an isentropic process following the variable specific heat analysis, or what we call actually the exact analysis. In this case, this term will be 0. Then we can equate this equation to 0. If we equate this equation to 0, then we can get actually a relation for the pressure exchange between the final state and the initial state. Is that clear, ya shabab? Are you following?
Yes.
So yeah, it's a simple. Just we have lot. I'm just trying to derive it for you, but we don't have that much talk about all of this equation. It's a very simple. So just equate this equation to 0. So it will be R or ln B2 over B1 will equal to, actually we can take this to the other side, so it will be S naught 2 minus S naught 1 divided by R in this case. Okay. Right. Can we get B2 over B1? Here we have ln. Then we can take the exponential of both sides. So exponential will go with ln here. Then we can say B2 over B1 will equal to exponential of S naught 2 divided by R minus exponential of S naught 1 divided by R. Is it?
Yes.
So exponential of S naught 2 divided by R minus exponential of S naught 1 divided by R. But if we have exponential of term minus exponential of other term, is it the division? So it is equal to what? Exponential of S naught 2 divided by R. This is divided by the exponential of S naught 1 divided by R. Is it, shabab? So is it okay?
Yes, right.
So this equation, this is just mathematics. So we can just say this term exponential of S naught 2 divided by R. We can call it actually as relative pressure V2. And the exponential of S naught 1 divided by R, we call it actually as B relative 1. And in this case, we can say V2 over B1 will equal to the relative pressure V2 divided by the relative pressure B1. But if we have a gas undergo, let's say, a process from 1 to 2, ideal gas, we can apply BV is equal to RT at both states. Then we can say V1 divided by T1 will equal to V2 divided by what, shabab? Divided by T2. But can we get the relation of V2 divided by V1? V2 over V1 will equal to what? Will equal to B1 divided by V2 multiplied by T2 divided by T1. Okay? Is that clear, shabab? So V2, based on this equation, we can just say V2 over V1 will equal to B1 over B2 multiplied by T2 over T1. But B1 over B2 is the same as B relative 1 divided by B relative 2. So V2 over V1 will equal to B relative 1 divided by B relative 2 multiplied by T2 over T1. We can call this ratio T2 over B relative 2 as actually as V relative 2. And the T1 divided by B relative 1, we can call it as V relative 1. And based on this, we can say V2 over V1 for an ideal gas undergo an isentropic process will equal to V relative 2 divided by V relative 1. So if we have an ideal gas undergo an isentropic process following the exact analysis, in this case we have two equations. The first one, which state actually that the ratio B2 over B1 is the same as B relative 2 over B relative 1. This is the relative pressure, not the reduced pressure. When we talk about the compressibility chart, this is something else. So this is the first equation. The second equation, which states V2 over V1, the ratio of the volume, is equal to V relative 2 over V relative 1. And this is actually the second relation. Based on the definition that T divided by B relative, we define it as V relative in this case. But in this case, from where we can get actually B relative and V relative. B relative and V relative, those are actually only available for air. we usually say from table A17 to table A25, but actually those properties B relative and V relative are only listed in table A17, so they are only available for the case of if the working fluid is air. طيب in this case what should we do يا شباب? If we have a compressor which is compressing air, okay? If he give you the condition at the inlet of the compressor, give you pressure and temperature, and they give you the final pressure, and I need to calculate the final temperature. So what should I do in this case? So from table A17, if you look at the given temperature, you will find the internal energy is given as we used to do. Enthalpy is given. You will find the S naught is given, and also you will find the relative pressure and also the relative specific volume. Okay. So at a given temperature, we can go to the table and get relative pressure and relative specific volume. But those two values, شباب, relative pressure and relative specific volume, are only applied when we have air undergo an isentropic process. Okay, those values are only applied in this case. But if B1 and T1 are given at the inlet of the compressor and the pressure B2 is given, and I need to calculate the final temperature T2, following the exact B relative 1. Okay, so if I have B2 is given and B1 is given, then we can say B relative 2 over B relative 1 will be the same as B2 over B1. Then I can calculate B relative 2, which will equal to B2 over B1 multiplied by B relative 1, which I got actually as the temperature T1. So calculate B relative 2, go to the table back, then we can calculate the final temperature T2. But if he give you, instead of pressure, give you the volume, the initial volume and the final volume, in addition to the initial temperature, the inlet temperature. So with the inlet temperature T1, I can go to the table A17, I can get V relative 1. Then I can calculate V relative 2, which will equal to V relative 1 multiplied by V2 over V1, based on the second relation. Then I can calculate, go to the table with V relative 2, go back, then I can calculate temperature T2. This is the exact analysis. Now look here at this example. This example may give you actually a clear indication about this.
Doctor,
Yes.
V, we are talking about specific volume, right?
It doesn't matter if it is a closed system, so it doesn't matter the specific volume or the total volume. Okay. So let's look here about this example. So most of the cases we are talking about the total volume. Okay. But for closed system, it can be here. It is written here. For closed system, we can consider it as a specific volume as well because the mass is constant. طيب here شباب, he said we have air is compressed in an engine car, like the internal combustion engine in the car. Air is compressed from 22 degrees C and 95 kilopascal, which is atmospheric condition, in a reversible and adiabatic manner. What does it mean, شباب, reversible adiabatic?
Change in entropy is 0.
Yes, isentropic, reversible and adiabatic. This is the definition of the isentropic process. So isentropic, that means delta S is 0. So that means we have an ideal gas, which is air, undergo an isentropic process. And he gave us here the compression ratio, the volume ratio between the final state and the initial state, which is equal to 8. And we need to determine the final temperature in this case. So in this case, شباب, volume V2 and V1 are given. So in this case, I will be calculating what? V relative or B relative? V relative in this case. So temperature T1, I will go to the table, get V relative 1. Then I can calculate V relative 2 as the process is isentropic, which is V2 over V1 multiplied by V relative 1. Then in this case, I can go to the table back with V relative 2 and calculate the temperature T2. Here V2 over V1 is given. So at T1, 295, you can check those values from table A17. Then I can get V relative 1. Then we can calculate V relative 2 based on this ratio. V relative 2 is equal to V relative 1 multiplied by V2 over V1. V2 over V1 is 1 over V8 because V1 over V2 is given equal to 8. So V2 over V1 equal to 1 over 8. Multiplied by V relative 1, then I can calculate V relative 2. Take this value and go to the table back. So at this V relative 2, this value, I can go to the table, then I can get the temperature in this case. Okay, so when we have an isentropic process, يا شباب, ideal gas undergo an isentropic process, we have to be to decide first. We'll be using actually the exact analysis based on B relative and V relative. Inshallah, we'll learn this how to use this when we calculate the isentropic efficiency of the compressor. We will be using actually the isentropic process of an ideal gas. You have to decide either it is exact analysis, variable specific heat, which is this analysis, or it is actually the approximate analysis or the constant specific heat analysis. This is the exact analysis using actually the table A17. This is the approximate analysis or the constant specific heat analysis. We can relate the temperature, pressure, volume change through this relation, which we have developed based on equating this equation to 0, delta S is equal to 0. Here's the second example, shabab, is for this case, following the approximate analysis. So this example 6, is based on the exact analysis. Example 7 is based on the approximate analysis. Type approximate analysis, he said here we have helium. So we have the working fluid is gas, which is helium. Helium gas is compressed in an adiabatic compressor from the initial state, 14 psi, which is pound per square inch. This pressure is a unit for pressure used in the English system of unit. It is used in the car tires. Usually the car tire pressure, when you go to the puncture to set the car tire pressure, it should be about 35 psi. 1 psi is about 14.5 bar. So it's about 2 bar. 35 psi, pound per square inch, which is the car tire pressure, is about 2 bar. So the pressure of the air inside the car tire is about 2 bar. So this is the psi, pound per square inch, and the temperature is given in Fahrenheit. To a final temperature 320. So helium is compressed in a compressor from this pressure and temperature to a final temperature. Okay, in a reversible manner. Okay, what does it mean reversible? He said here adiabatic compressor, so heat transfer is 0. And reversible, so reversible adiabatic, that means what, shabab? Isentropic. So delta S is equal to 0. In this problem, he said reversible and adiabatic system. Here also, he said adiabatic compressor and he said in a reversible manner. So reversible and adiabatic means isentropic. So delta S is equal to 0. By following, let's solve this problem following the approximate analysis. Then we need to calculate the final pressure of helium. So we can say B2 over B1 will equal to T2 over T1 to the power K over K minus 1, which is this relationship. So we can say B2 over B1, we can take this exponent, we can take it to the other side, flip it. So B2 over B1 will equal to T2 over T1 to the power K divided by K minus 1. But from where I can get K, shabab? From where we can get K? The value of K, which is the specific heat ratio from table A to B. But actually in table A to B, helium is not there. So you can just check in table A to A, which gives the value of a specific heat and the specific heat ratio at average temperature equal to 300. So from this table, usually K is not mainly function of temperature. Usually it is a constant value, so it does not affect much with temperature. So we can take this value from table A to A for helium. It will equal to 1.6 something. Then we can just apply. We have B2 and B1. And we need actually, we have T2 and T1, and we have B1, then we can calculate B2. But take care here, ya shabab. The temperature should be what? This is the English system. Temperature in Fahrenheit. The temperature here should be the absolute value. The absolute temperature in the English system is calculated in Rankine. Okay? It will not come to your exam. Rankine is equivalent to Kelvin. Fahrenheit is equivalent to degrees Celsius. Okay, so you have something here. You can just convert this Fahrenheit to degrees C. We have the temperature in degree Fahrenheit is equal to 1.8 multiplied by the temperature in degree C plus 32. You can convert it to degrees Celsius, and then you can convert it from Celsius to Kelvin, and then you can use Kelvin here. Or you can convert it from Fahrenheit to absolute scale in the English system, which is the Rankine scale. Then we can calculate it. But in your exam, I will be just stick to the SI system. Okay, but this is what does it mean R here. R is the Rankine scale, which is equivalent to the Kelvin scale in the SI system. Is that clear, Shabab?
Yes, clear.
طيب, so just to summarize here, I just give you how to calculate delta S for an ideal gas. Following the constant specific heat analysis, we have developed those two relations. You have to keep in mind. We have learned how to calculate CV average and CB average, then you are able to calculate delta S of an ideal gas following the constant specific heat analysis. For the variable specific heat, we have considered this equation to calculate delta S. S naught 2 and S naught 1 we can get from table A17 to table A25, and then we have to add here minus R ln B2 over V1, B2 over B1 to calculate delta S. Okay, this is how to calculate delta S of an ideal gas. But we said if we have an ideal gas undergo an isentropic process, we just equate the equation to 0. Then we get the relation. This is based on the approximate analysis variable specific heat. We get this relation between temperature, pressure, and volume. How does it change? And for the constant for variable specific heat analysis, or we call it the exact approach, we have developed those two relations and as a function of the relative pressure. Then in this case, if you are giving the temperature, you can go to the table, get the relative specific volume or relative pressure depending on actually what is given. If pressure is given, I will get B relative pressure. If volume ratio is given, I will get V relative, and in this case, I can get the final condition. Okay, in terms of temperature and the pressure. Okay. Type. Let's consider another topic here. We said if we have a system undergo an isentropic process. Isentropic process means this process is reversible and adiabatic. Reversible, that means actually we don't have any kind of losses within the system. Like if we don't have any kind of losses, that means the work in this case should be the maximum work, or we call it actually as the reversible work. In case when we have an isentropic process. But how we can calculate this reversible work? We call it reversible steady flow work. Steady flow means that the system is open or closed?
Open.
Open, so we have a steady flow, that means we have flow in this case. So let's see how we can calculate the reversible steady flow. Reversible steady flow work when we have a reversible process. So that means the work in this case is maximum. But let's consider an open system, any open system. That open system, as it is open, so it allows for energy transfer and also it allows for mass transfer. Let's consider this system undergo a reversible process from one initial state to a final state. So this process is reversible. So that means we don't have any kind of losses. But let's summarize the first law equation. We can say delta Q minus delta work in the specific form, a specific and differential form. That should equal to delta H plus a change in kinetic energy plus a change in potential energy. Is it, Shabab? So we said Q dot minus work dot based on chapter 5 equal to M dot multiplied by delta H plus a change in kinetic plus a change in potential. Just I divide the two sides by M dot, then I get the specific form. So it will be Q minus work equal to change of enthalpy plus a change in kinetic plus a change in potential. Then I just consider the differential form. We are considering the element in this case. But this process is reversible, so this delta Q reversible, and this work is the reversible work or the maximum work. But by definition of delta S, we said delta S is equal to delta Q over T by the condition that what? That this process is reversible. Or we can say TDS or delta Q reversible will equal to TDS, delta Q will equal to TDS. But based on the TDS relations that we have developed, delta Q is equal to TDS and TDS is equal to delta H minus VdV. This is the TDS, the second TDS relation. We said TDS is equal to delta H minus VdV. We have developed this one last time. So we can replace this delta Q by TDS. And TDS is equal to delta H minus VdV. So this term is delta H minus VdV. But we have delta H here, so this delta H will go with this delta H. Is it, Shabab? Then we can take this term, yes, take this term, negative sign, take it to the other side with positive sign, then we can say minus delta work reversible will equal to minus VdV. It transfer to the other side, it will be positive. This negative here, take it to the other side, it will be positive. Plus the change actually in kinetic energy, plus the change in the potential energy. Okay? Or we can just multiply the whole equation by negative sign. So instead of minus delta work, it will be positive delta work, and you can have negative sign here. The whole equation will be negative in this case. But if we have the kinetic and the potential energies, those two terms are neglected. If we neglected them, in many applications we neglect the change in kinetic and the potential energy with respect to the change of enthalpy, and the change of enthalpy is equal to, in this case, is function of pressure in this case. So that means the reversible steady flow work will equal to minus VdB. Or we can say, if we integrate, then we can say the reversible work will equal to integration of VdB. This is in case of what, in case of open system. Okay, so in case of open system, the work is equal to what? Integration of what? VdB. But do you remember for closed system, we said work is equal to integration of what? Integration of VdV. This is for closed system. But this is actually for what? For open system. And this is the difference. In case of closed system, work is equal to integration of VdV. And we have proved this relation in chapter 4. Now we are proving that the case is reversed in case of open system. In case of open system, the work is equal to what? Integration of what, of VdV. Integration of VdB in this case. Okay? Yes.
The work for open system, but not reversible, is the same?
It should be in this case. It depends actually on this process. It will be the same integration, but the process is reversible. In case of reversible, I will solve an example with you to show you this case. Okay, but it should be the same. We have learned in chapter 5, if we have, let's say, a compressor, how we can calculate the work of a compressor. Q dot minus work dot is equal to M dot multiplied by what? H2 minus H1. If the system is adiabatic, Q dot minus work dot, so the heat transfer will be 0. So it will be work dot is equal to M dot multiplied by delta H. How we can calculate delta H? H2 and H1? From the table, if we are talking about steam, let's say steam turbine, H1 and H2. From the table, I will give you pressure B1, temperature T1, then I can get H1. If the process is isentropic or reversible, then in this case I can say S2 is the same as S1. And then I can give you the pressure, let's say B2, we have solved the example last time, like this one. If the process is isentropic, I will go to the table and I will calculate H2. But in both cases, if it is isentropic, which is reversible or not, it is actual one, it doesn't matter in this case. So if it is isentropic, I will say S2 minus S1. And then I will calculate H2. But in both cases, we use the same equation. Work is equal to M dot multiplied by delta H in this case. Okay, Shabab? But let's consider this equation. Get back to this equation and do the integration. And let's add also the change in kinetic. Don't neglect them, just leave them. Because I will show you now a link between this. This is coming from the energy equation, first law of thermodynamics. I will just remember you with another equation, which you have taken actually early at the early stage in the engineering. So here we can say delta Q, if I integrate, then I can say the reversible steady flow work will equal to integration of minus VdV, and then we can integrate for the kinetic energy. It equal to the change in kinetic energy minus the total change in the potential energy in this case. Okay. But if we have incompressible substance, what does it mean incompressible, Shabab? Incompressible density is constant, which is 1 over a specific volume. So the specific volume is constant. So specific volume is constant, like the case of what, Shabab? If we have a pump is pumping liquid water in most of the cases. Liquid water is incompressible substance, so volume is constant. So in this case, the work reversible or maximum work input to the pump will equal to what? We can take the specific volume outside, so the reversible work will equal to minus V as it is constant multiplied by integration of delta V, which is B2 minus B1, minus the change in kinetic energy, which is V2 squared minus V1 squared divided by 2, minus the change in the potential energy in this case. If those two terms are neglected, for a pump, then we can calculate the maximum reversible work input to the pump will equal to minus V multiplied by V2 over V1. Okay, so this is for a pump. Incompressible solids. But if we have just a flow inside a tube, we have just a flow. This flow is moving from cross section 1 to cross section 2. As we have a flow, so we don't have work. Okay, so in this case, just we have a flow, so we don't have work in this case. Work is equal to 0. So that means those three terms will equal to what? 0. Specific volume is equal to 1 over rho. That means V2 minus V1 over rho plus a change in kinetic energy V2 squared minus V1 squared divided by 2 plus J multiplied by Z2 minus Z1. All of this will equal to 0. This is the difference between its energy between state 2 and state 1. Or we can say the energy at state 2 will equal to the energy at state 1. Or we can say in general V over rho plus V squared over 2 plus GZ will equal to constant at any cross section. Have you seen this equation before? This is what?
In physics.
Yes, this equation is what? Is the Bernoulli's equation. So if we have a flow in mobile moving from section 1 to section 2, based on the reversible, because Bernoulli equation is applied under the reversible condition. We don't have any kind of losses. We assume we don't have any kind of losses. And based on this, we calculate the reversible work. But for a flow inside a pipe, we don't have reversible work. Just we have a flow. We don't have any kind of work. And that means those three terms will equal to 0. Then we can generate the Bernoulli equation. Bernoulli equation is applied for a flow that does not have any kind of losses. We don't have any kind of friction. That means the energy will be, total energy will be fixed from one section to another section. Is that clear, يا شباب?
Yes.
طيب, let's the quiz don't care about it, يا شباب. It's very simple. Yeah. But I will just give you this example. I will move on it with you. So here is this example. He said determine the compressor input work required to drive a compressor. This compressor is handling steam in this case. Okay, this steam it is compressed first of all isentropically. So isentropic, that means the work is reversible work. We don't have any kind of losses. From pressure 100 kilopascal to pressure equal to 1 megapascal. Assuming actually the steam is coming in as first case, we assume the steam is coming as saturated liquid. So in this case, instead of compressor, we'll bring a pump in this case, because pump is dealing with liquid. We have saturated liquid steam coming at state 1 at pressure equal to 100 kilopascal, compressed inside a pump, and then to the outlet pressure equal to 1 megapascal. Do you remember, Shabab, when I talk about the cycle, and I told you we cannot remove the condenser, because in this case we will have a mixture of liquid plus vapor, and in this case I have to use a compressor if I removed the condenser. Do you remember, Fahdi, you asked about this? You said why we don't remove the condenser, and in this case we can just take the mixture of liquid plus vapor steam, and then we can compress it inside the pump. And I told you to use a compressor to have the same pressure to compress a fluid for the same pressure ratio. In this case, actually the power required to drive the compressor will be very high in this case. So it is better to condensate water first, then you can use a pump. Now we have this example is here. We need to compress the steam from pressure equal to 100 kilopascal to another pressure equal to 1 megapascal. But one case this steam is coming as saturated liquid, so it is liquid water, and the other case it is coming actually as saturated vapor. It is as a vapor in this case. And in this case I need to calculate the power input that is required actually to raise the pressure from 100 kilopascal to 1 megapascal in both cases. So in both cases, we have the same pressure. We need this fluid to be compressed to the same pressure 1 megapascal. But if I use the pump is incompressible, dealing with liquid, coming saturated liquid, so it is incompressible. Type we have steam coming at pressure 100 kilopascal in this case, and it is coming as saturated liquid. Saturated liquid means what, Shabab? The volume will equal to what? V fluid at this pressure from steam table A5, we can get this volume. But we said, Shabab, in case of incompressible substance, which is the case of pump, which is liquid water, volume will be, a specific volume will be constant. Neglecting kinetic and the potential energy, so that means the reversible work will equal to the specific volume multiplied by the pressure difference. A specific volume I got at state 1, saturated liquid at this pressure, then the work required to drive this pump is equal to the specific volume multiplied by what? B2 minus B1. If you calculate this work, it is around 1 kilojoule per kilogram. So now look, if we need to compress this fluid, but it is coming, the same amount of fluid, but coming actually in the vapor form. Instead of saturated liquid, it is coming as saturated vapor in this case. Okay? So look here. So in this case, the reversible work will equal to integration of VdV. So in this case, the specific volume is not constant. Okay? Let me just do it for you. For the reversible, for the case of gas, the reversible work will equal to integration of VdV. Reversible work will equal to integration of VdV. Or we can consider it as, do you remember the equation for the compressor? We said what, how to calculate the work. Work is equal to what? From chapter 5, specific work. We said Q minus work is equal to what? H2 minus H1, is it? So in this case, we assume here the process is reversible adiabatic isentropic, so we don't have heat transfer. So the work will equal to what, Shabab? H2 minus H1. It is negative sign, we know. This is the work input to the compressor, it should be negative sign. So the absolute value of the work will equal to what? H2 minus H1. As I told you, it doesn't matter, it is reversible or irreversible. In this case, I will go to the table at state 1, pressure is given and it is saturated vapor, so H1 is equal to H gas. But how I can get actually H2 as it is isentropic, then we can say S2 is the same as S1 and we have B2, then I can calculate H2. So you can check about these values. Then we can say the work will equal to H2 minus what? H2 minus H1. Another way, if it is isentropic, so it is equal to integration of VdV. But we said TdS is equal to delta H minus VdV. And the process is isentropic, so delta S is 0. To TdS, this term will be 0. So delta H will equal to what, Shabab? Will equal to VdV. And the reversible work is integration of VdV. So we can replace VdV by what? By delta H. So it will equal to integration of delta H, which is H2 minus H1, which is the same equation that we have developed in chapter 5. Okay? So it doesn't matter, either the process is reversible or not reversible. At the end, the work will equal to H2 minus H1. Now I have calculated here the work, Shabab. H2 and H1 based on when the substance is gas. So look at the value, Shabab, here. Value is equal to what?
500.
And the one in case of liquid?
1.
About 1 kilojoule. So you can see it's 500 times. So to compress the same amount of substance between the same pressure values, in this case, if it is liquid, the power required to drive the pump is much less than the case if the fluid is actually gas. Why is this, Shabab? Because of the volume of the gas. Gas actually have a higher volume in this case. So to compress the gas, we have to apply actually more work in this case. And that's why we cannot just get rid of actually the condenser. It is better actually to convert the steam, leaving the steam turbine to liquid. Then in this case, I can drive the pump actually with very small amount of input power in this case, because pump or compressor are consuming work. And you can look at this, Shabab, from the HS diagram, from the Molière diagram. If you look at this process, on the HS diagram for the two cases. Let's look at it on the HS diagram. This is the saturation curve, and this is the line of pressure B2. This is the line of pressure B1. Usually the pressure has a steep gradient here, okay? So if it is saturated liquid, you can look here between the two lines of pressure. So this is the state 1 and the state 2. And the process is isentropic, so it is just a vertical representation from state 1 to state 2. If it is saturated liquid, this is the liquid state. We said in the Mollier diagram, this difference gives us indication about the value of what? Of delta H. And delta H gives us indication about what, about the work. So if delta H is high, the work should be high. In this case, as it is liquid, delta H is small. But look here, if it is gas, then in this case for isentropic process, that should be the difference delta H in this case. Delta H is high in this case, so the input work should be higher in this case. Is that clear? Is it clear, Shabab?
Yes.